Interpretation of probabilities is often not so simple, and in this chapter we're going to look at typical situations where people often misunderstand the probability and draw completely wrong conclusions. And I'm talking here also about professionals in their field. They have some probability, but they don't realize what it really means. So let us start with example 1, which is about foreigners and criminality. Please read it and have a look at the tree, and let's then find the probability that a randomly chosen person is a non-criminal Swiss. The tree describes the situation. We have the total population, and out of the total population, 99% are not criminal and 1% is criminal. Of the non-criminals, 76% are Swiss and 24% are foreigners. Of the criminals, 48% are Swiss and 52% are foreigners. Let's now find the probability that a randomly chosen person is a non-criminal Swiss, and this is 75.29%. Well, how did we calculate that? It's this probability times this probability. Let us now find also the probabilities for the rest. The probability that a randomly chosen person is a non-criminal foreigner is 23.77%, that it is a criminal Swiss is 0.45%, and the probability that it is a criminal foreigner is 0.49%. Now your task is to find the probability that a randomly chosen person is a Swiss, and then the probability that a randomly chosen person is a foreigner. Stop the film, and here comes the result. The probability that a person is a Swiss is this probability plus this probability, so it's 75.74%. And the probability for a foreigner, we can add these two, or just say it's 1 minus the probability of a Swiss, so 24.26%. The next task is to invert this upper tree here. And by inverting, we mean switch the first level and the second level of the tree. So think for a moment what this means, what we have to fill in into all these empty boxes. Stop the film for a moment. And here comes the result. The starting node is still the population, and then the first level is Swiss and foreigner, and then on the next level we have this not criminal and criminal for the Swiss and for the foreigner separate. Now the next task is fill in the probabilities. Try that on your own again. Stop the film. Here come some hint if you have not yet managed. Fill in first these probabilities, then fill in the leaves down here, and then find these probabilities. Stop the film, and here comes the result. We get the probabilities of the first two branches here from this up here, which we calculated in B. The leaves have the same probability like in the upper tree. We just have to find the corresponding leaves. So this is the non-criminal Swiss, corresponds to this one. This is the criminal Swiss, so corresponds to this here. The non-criminal foreigner corresponds to that here. And the criminal foreigner corresponds to this one here. Now we need to find the probability of this branch. Well, we know that this probability times this probability here is this, so we can calculate it backwards as 0.7529 divided by 0.7574, and we get 0.9941 for this branch, and hence 0.0059 for this branch, since the two have to sum up to 1. To find the probability of this branch, we calculate again this 0.2377 divided by this 0.2426, and we get 0.9798, and hence 0.0202 for this branch. So now we can answer the following question. What is the probability that a randomly chosen foreigner is a criminal? Answer it by yourself. Stop the film. And here comes the result. The probability that we're asking for is the probability that somebody is a criminal given that that person is a foreigner. And we can read off this probability in our tree as the probability of this branch here. So the probability is 2%. When people state that half of the foreigners are criminals, what probabilities do they mix up? Stop the film and answer it yourself. Well, they mix up the probability of nationality given that somebody is a criminal and the probability of being criminal given the nationality. 52% of the criminals are foreigners, yes, but only 2% of the foreigners are criminals. In the last step, let us find the probability of criminal given foreigner using the laws of probability. We will now need the definition of the conditional probability a lot. So P of A given B is the probability of A and B divided by the probability of B. And we can also write the probability of A and B as probability of A given B times the probability of B. So the probability of criminal given foreigner is the probability of criminal and foreigner divided by probability of foreigner. The probability of criminal and foreigner can be written as probability of foreigner given criminal times probability of criminal. And the probability of foreigner can be split into probability of foreigner and criminal plus the probability of foreigner and not criminal. So we copy the numerator, and in the denominator, probability of foreigner and criminal, well, that's the same what we did up here. So we get again this here, and the probability of foreigner and not criminal is the probability of foreigner given not criminal times the probability not criminal. And all the probabilities mentioned here can now be read off from the original task, from the original tree. And we get this expression, and using the calculator we find that it's approximately 2%. Note that all that we do during this calculation is all the things that we have done also when calculating the tree. For example, this here is the way that we calculated the leaf, foreigner and criminal. And here that's the way that we calculated foreigner and non-criminal. Then by adding up these two, that's the way that we found the probability that somebody is a foreigner. And this is how we found the probability of the leaf, foreigner and criminal. And in the end, to find this probability here, we divided this probability, so the probability of foreigner and criminal, with this probability up here, the probability of a foreigner. Let's look now at a real-life example with real-life data. Trisomy 21 occurs in approximately 0.2% of all pregnancies. There is a very reliable test to find out whether the child has trisomy 21. If it has trisomy 21, it will show that with 100% precision, and if it doesn't have trisomy 21, the test will be correct in 99.9% of all the cases. So it seems obvious that once you have done the test, you get very precise information, and you can then decide about abortion or not, depending on your personal attitude to life. Let us now find all related probabilities using a tree. First, fill in the boxes here of the tree. Stop the film, and here comes the result. Your tree should look something like this. Please note that test positive is not meant morally positive, but in medicine it means that the test shows that what you have asked for. So here we ask for, is there trisomy 21? Test positive means it says yes, there is trisomy 21. Now complete the probabilities. This means fill in the probabilities of the different branches and the probability of the leaf here. So for example here it means probability that there is trisomy 21 in reality and the test is positive. By the way, the first level in our tree is the reality and the second level is the test. Stop the film now, and here comes the result. Now answer question B. Stop the film, and here comes the result.
It is the probability of trisomy 21 given that the test is positive. So what is the probability that my child has real trisomy 21 if the test says so? Well, try to answer that, give it a guess, and we'll calculate it now. Solve task C, stop the film, and here comes the result. To find the probability that the test will be positive, we have to add the probability that the test is positive and there is trisomy 21, and the probability that the test is positive and there is no trisomy 21. And the same for test negative, but one of them is 0, so we just get this second number here. Task D, you have to invert the tree. In this tree, let us use rounded probabilities. So instead of this number, let's use just 0.001, and let us round this also just to 0.997. And then also here, this will be 0.997, and this is rounded 0.003. Now start with filling in the empty boxes. Stop the film, and the result comes here. The first level of the tree is now the test result, and the second level is the reality. Now complete the probabilities into the tree, so all the branches and also the probability of the leaves. Again, stop the film, and here comes the result. These two probabilities are the ones calculated in number C, and since this leaf corresponds exactly to that one, they have the same probability, and this leaf corresponds to this one, so that way we find all these probabilities down here, and in the end, to find this probability, we have to take this probability divided by this, and here this divided by this yields this probability here. And now the question is, what is the probability that parents-to-be are actually interested in? Solve it on your own, stop the film, and here comes the result. Well, and we find this is the probability, namely the probability that the child has trisomy when the test is positive, or we can also look at this probability, the probability that the child does not have trisomy, even though the test is positive. And that's actually surprising. This probability is 1/3, which is quite high. And it's especially surprising when we compare it to the original test where we thought it's a very good test. It is actually. So what is actually the problem? Well, the problem is that trisomy 21 is a very rare disease. So even so, the test is very good because it has some small mistake probability in the cases when there is no trisomy 21. This makes this effect that we don't know so much for sure when the test is positive whether the child has trisomy 21 or not. In task E, find this probability that the child has trisomy 21 given that the test is positive using the laws of probability. You can proceed in the same way as we did in example 1, so try it on your own and stop the film. Here comes the result. So we get again for this probability approximately 2/3. What we have found in these last two examples is the so-called Bayes theorem. It states how we can find the conditional probability of A given B if what we know is the conditional probability of B given A and B given A complement, and additionally if we know the probability of A. This is very often very handy because there are often situations where we have exactly this situation. The proof of the theorem is exactly what we have done before, so we get the probability of A given B is by definition the probability of A and B divided by the probability of B. We can rewrite the probability of A and B as the probability of B given A times the probability of A, and the probability of B as probability of B and A plus probability of B and A complement. And then P of the probability of B and A is again probability of B given A times probability of A, and probability of B and A complement is probability of B given A complement times probability of A complement which is exactly what we wanted to show. Now apply this theorem to solve example 3. Stop the film, and here comes the solution. We are looking for the probability that a mail is spam given that the word sex appears in the subject. So now we apply Bayes' theorem. We find that the probability is approximately 92%, which is less than the 95% required, so it will not be classified as spam. Here comes now a small add-on that you may also skip, but don't skip then example 5. Let us look directly at example 4, which will help us then to understand actually what this formula up here says. Read the text of the example, and when you're done, continue the film. We want to find the probability that the outcome of the rolling the dice was an A, given that finally a white ball was drawn. The probability that the result of the rolling the dice was an A, given that the final ball drawn was white, is just probability of A and white divided by probability of white. This is the definition of the conditional probability again. The probability of A and white is just probability of white given A times the probability of A, as we have seen before several times. And the probability of white consists of the probability of A and white, which I can write in this way, plus the probability of B and white, which I can write as probability of white given B times probability of B, plus the probability of C and white, which I can write as probability of white given C times probability of C. So you see that this is just a generalization of the original way we wrote down the Bayes theorem. And A, B, and C are called a partition of the sample space because they form together the whole sample space and they are mutually exclusive. If the result of rolling the dice was A, it can't have been a B or a C, and so on. Inserting the probabilities, we get this expression, and in the end we get for the numerator 1 divided by 6, and for the denominator 3 divided by 4. So 3 divided by 4 is the probability of getting a white ball in this experiment. The probability that the dice was a B if the ball obtained is white can be calculated as probability of white given B times the probability of B divided by the probability of white, and this probability of white we just said before is 3/4, so we get 3/4 times 1/3 divided by 3/4. Note that this expression is this one here in the center, and we get a probability of 1/3 here. Let's now look at probability of C given white, and note that the expression here in the numerator is the last expression of here in the denominator, and we get 4 divided by 9. So our best guess is to guess that the result was a C with a probability of 4 divided by 9, which means 44.4%. Last but not least, I want to present to you this famous goat problem here in example 5. There is a TV show with 3 doors that are closed. Behind one of the doors there is a car hidden. Behind the other 2 there are goats. Once the candidate selects a door, the quizmaster opens one of the other 2 doors, but it will be always a door where there is a goat behind. He knows where the car is, so he will for sure not open the door where the car is behind, and he will not open the door that the candidate has chosen. And then the candidate has another possibility to change his mind and switch the door, or he can stay with the door he chose in the beginning. And the question is, what is the best strategy? Should the candidate stay with the door he chose? Should he switch, or doesn't it matter? So have fun. I will not tell you the result here, but only live.